Hello, good day, and welcome back to Duplicate Consults. Today, we'll be working together to see how we can properly analyze and design for our beams and our columns. Keep in mind that prior to this lecture, we've seen how we could transform a single piece of architectural drawing into a 3D realistic model, and we went ahead to analyze and design for the slabs. In case you missed out on those, kindly check the link in the descriptions and you'll be able to find the step-by-step process on how we were able to get to this very level. And without wasting much time, let's jump right into what we have for today. And like I said earlier, today we'll be looking at the analysis and design of our beams and columns. To design our beam and column sections, we'll come to analysis and come to building analysis. Then we'll go back to this analysis tab, and you see we already have an existing building analysis. So the previous analysis which we did for the slab is still valid. So what we are concerned about in this case is our column slash wall reinforcement design and our beam reinforcement design. So this is for column and this is for wall. In case we have a shear wall on this structure, this will also try to run design for it. And this is for our beam reinforcement design. So I will tick this and I will tick this. And for this case, there's an option for reselect bar slash design. Let's assume that we've done a previous design, a previous column and beam reinforcement design for this very structure. Then after the design stage, we went ahead and made some modification. Let's say we increase the imposed load on that very beam. So if I don't tick this and I run this analysis, what it's going to do is it will try to design that very structure based on the previous reinforcement and the section that was provided. So it will only run the analysis to see if that previously provided sections are okay. But if we tick this, after we've increased, let's say that imposed load, in this very case, what it will do is it will try to check for it, and if it's not sufficient, it will redesign and reselect a new set of reinforcement for our column or our beam. But for this case, we've not done any previous beam or column reinforcement design, so I have to select it. So I will select this two. I will allow it to show my axial load comparison warnings, and I'll click on start to design for my columns and beams. So I'll click here and our analysis processes will start. So now we are done with our analysis, and this was done in just approximately 12 seconds. So let's close this and close this part. So let's come to the design. If we want to design, we'll come to concrete design, and let's start with the beam. Or what you can do is to design per story, you can come to story 1. When you come to story 1, expand this, come to beam, click on beam, right click, and there's an option for beam reinforcement design, and that has active story in brackets. So we'll click this. So these are the beams on this very story, and let's go ahead and open any of this. So we'll double click. So this process is called the process of interactive design. So what it helps you to do is makes you communicate with the design process, and you are able to make modifications to whatever the software has provided for you. So if you look at this part, we have our top bars. So these are our top bars, which is our top reinforcement. This is at the span moment, this is at the support moment. So in this case, it's provided two number of y16 to counter the moment at the top, and it provided two numbers of y16 also at the bottom. So in the real sense, let's look at what this is talking about. So what this means is, considering the load that is being imposed on that very beam, it has provided our top and bottom reinforcement for us. So it has provided two y16 at the top and provided two at the bottom. Although this picture is showing 4 here, but this is just an illustration of what we are talking about. And it has also provided our links with the spacing. So if we come back to our software, and we open up that beam, you can say these are our 2y16 for the top and the 2y16 for the bottom. So you can see the links here. This is 1y3 at 300. So that means we have these links provided at one of these links are provided at each 300 mm. So probably most important thing in this very stage is our utilization ratio or our U ratio. So our U ratio, if you look at, you see a couple of numbers here. So this is actually the measure of how close this very beam is to using its maximum capacity, both compression and tension capacity. So this is a measure of how close it is to use its maximum capacity. So to put it in a very clear context, let's look at this picture here. If you look at this first man, you can see that he has a maximum capacity of 30 kg and he's carrying a load of 20 kg. So this is the maximum he can carry, but at this very point, he's lifting a weight of 20 kg. And if we have to check the utilization ratio of this man, we can calculate this simply by dividing our 20 by our 30. So if we divide this 20 by 30, it gives us 0.67. So it means it's using about 67% of its capacity. So it can still carry more load. So what he's using is just about 67% of its maximal section capacity. So if you look at this other man as well, he has a total weight of 100 kg, but is actually lifting a 95 kg. So if we divide that's 95 by our 100, is actually using about 95% of his strength to lift this very weight. This maximum capacity we are talking about is the maximum capacity of both the reinforcements and the sections combined. So if you come back to our software, you will see that the utilization ratio of these beams, they all differ. So for this we have a 53% U ratio, and for this we have 52, but for this case we have about 99. And this case is not very safe. It is not okay, because in the process of design we are supposed to ensure, or we must ensure, our structure becomes robust. So it becomes robust in the sense that in case there are unexpected load which were not factored during this process of analysis, our structure can in turn still resist this load. But in this case where we use where our utilization ratio is up to 99, it will be very difficult for this beam to resist unexpected load. But if you ask me, an ideal utilization ratio for my own personal design, everybody is different. For my own personal design, I ensure it does not get more than 80%. 81%, 82%, 83 is quite okay, but I ensure it stays within the range of 80% at maximum, and sometimes 75%. It depends on the structure. So what can we do in cases that we have very high utilization ratio? We can improve the properties of that very beam by either increasing the section thickness, the section width, or we can increase or add more numbers of reinforcement. So for this case, let's say even with this design of 4y16 at the bottom and 2y16 at the top, just an example, we can decide to increase the top reinforcement to 4y16, so it also increases the area of steel provided, and that will in turn reduce our utilization ratio. So let's see how we can do that in the software. So I will click here. Then let's take an example of this one that has a very high utilization ratio of 90, a whooping 99%. So I will double click and see the reinforcement it has provided. Okay, so it has provided 2y16 at the top and 2y16, so 2y16 at the span moment and 2y25 at the support moment. So you always have to pay attention to this extra AS, because this is the area of steel that is provided extra above what was required. So let's say after our design, it requires 100 millimeters square, and we've provided 200. So what it means is that we have an extra 100 a whooping 100 as extra. So you always have to pay attention to this. Then for this case, still talking about our interactive design, we can see if we can reduce this. See, if we reduce to 2y20, you can see we've gotten to our extra, we've gotten our extra as minus. So let's see if we take this to 3y20. So our aim was to reduce the utilization ratio. So what we can do is let's try to increase these members and see if there will be any significant change. I will take this to 3y16, 3y16 and click OK. Okay, you can see I have gotten a utilization ratio of 83. So let's come back and try to reduce this a bit. So 3y16. So this is your process of design actually, and this is where you try to save your clients a lot of money. In this case, you should not in any way put finances first. What is what is very very important at this very phase is the robustness of your structure. So you have to think about safety before you consider cost. So let's say 4y16 and our extra AS here is just 59 and 31. This is not very advisable. It is always advisable you keep your extra AS let's say minimum of about 70 to 100. I prefer going with 100, or let's say anything above 70. I prefer going with that because that's like 50% of the capacity of each reinforcement. So I will let's go back. It has gone to 96%, but I want to stick with this 4y16. I don't want to go beyond this because I don't want the client to get 4y to get a different reinforcement size, which is the y20. So what can I do in this case? Let me even go ahead and reduce this and see what we have. We still have 96%. So I will reduce. It means reducing this does not really have any significant change. Okay, it does. Let's increase this and 96%. So what else can we do to uh, our section? If we've tried increasing the reinforcement and we want to stay between the range of y16 and this is not working, what we can do is we can try to increase the thickness of this very section to see if that can also help in countering the effect. So to do that, we'll come to this beam here. As you can see, this was designed for a thickness of 450. So this is our H, which is our thickness. It was designed for 450. So let's change this to 600, and I will change this to 600 as well. After doing this, you must have to click on this interactive design. So I'll for this very version, so I'll click on this interactive design. It has done my calculations. Okay, and let's close this. Okay, so you see it has reduced this from was it about 96% to about 66%. So let's come back and see. You see, so we still have our 2y16 here, our 4y16, 2y16, then 3 and 3. So you see we've increased the capacity of the concrete, so it has also helped in countering the effect of our movements. So let's see if we can further reduce this. Okay, 72% is not bad. And again, let's look at another critical consideration when we are designing for our beams. And this has to do with the reason why two structural engineers can design for one structure, the same modeling, the same analysis, everything, but another person will come out with a higher ton of reinforcement, while the other person will come out with a lesser ton of reinforcement. So to appreciate that, I will open up any long beam here. I see this has about, okay, let me open this one. And okay, these are the reinforcement provided. These are our top and bottom. So if you observe something, you will see that at this point, we have 2y16. We have 2y16 here as well. But coming to this point, we have 2y20. So let's try to bring this down to 2y16 and see what happens. You see, it's not sufficient. So to further understand what I want to explain here, I will open up the bending moment and shear force diagram just for a few seconds. So to do that, let's come to diagrams. Now, observing our moment diagram, I want to point out that all these points where we have these red lines, these are our column positions. These are our grid lines where we have our columns. And if you observe, we have a hugging moment here. This is going up. Then when it comes to this point, it goes down. Then it comes back up here. So these are known as our sagging moments, while these other one are known as our hugging moments. So you agree with me that we have our hugging moment at the column positions. You see, we also have another hugging moment at these other column positions, same here and same at this very point. So it means at the column position, we'll be requiring more numbers of reinforcement, possibly we'll be requiring more numbers of reinforcement at the top. We will be requiring more numbers of top bar at the column positions, while at the span we will require more numbers of reinforcement at the bottom. And with that understanding, let's exit this part. Let's speak to our top bar now. These are our top bar, the top bar and the supporting top bar. They are both the top bars. So you see, we have, this is the first column positions. We have 2y16. At this point, we have 2y16. That is for the mid span. Then coming to these other column positions, we have 3y16. So this is because of the high hugging moment at that very column position. That is why we are having this 3y16 at the top. So let's go ahead and reduce this. So if you reduce this number to 2, you can see it's not sufficient. What we can do when we get to site is, so if you take a look at this video, this is our column point. No, this is our column point. So this is a different design actually. And at this column point, you can see we have 1, 2, 3, 4. We have 4 numbers of top bars. This is y25 and these are y16. So we have 2y16 and we have 2y25 at the top. And when we move from the column points coming to the midspan, you can see this has been reduced to 2 numbers of y16 because basically we don't have moments at this very point. So we can continue in that regard, getting close to our column. That's the position of our hugging moments. You can see we've also increased the number of reinforcements to 2y25 and 2y16, and we can still maintain that just after the column position, some distance to the right, and we'll get to do more about this when we get to the detailing phase. So this is one of the things that can help you to reduce your number of reinforcement. So when some person, what they do is the moment they say these 4 numbers of reinforcement, which consist of 2y16 and 2y25, they will choose to run this beam all across the full span. They will choose to run this reinforcement rather all along the full span of this very beam, and this is what leads to over design. Do not forget that it is better you under design than to over design, because when you under design, at least it will show you signs of failure before it will finally fail. When you over design, you will get to find out that your buildings might even collapse without giving you any sign. So it is better to under design. So like I said earlier, this is the reason why two structural engineers can design the same structure. Some persons will have lesser tons of reinforcement, while the other persons will have a very high ton of reinforcement. So coming back to our software, so we see 2y16 here. This is okay. 2y16 is okay. And at this point, it has provided 2y20. So let's say at this support, 2y16 is not sufficient. We can choose to increase this to 3y16. So like as I was saying, some persons might decide to just run everything to be 3y16 instead of cutting them halfway, and it leads to over design. Aside the fact that this is not economical, like I said earlier, this can lead to collapse of our building without giving us any prior signal. So if this is clear, and if this is clear at this point, I will go ahead and just close this up. So there are other things I also want us to look at this very point, aside from the utilization ratio, let's go back up and open this very beam. So if you look at this point, this S bar top, if you see we have here 32. Always ensure that this does not go beyond 20, because this is speaking about the spaces between our reinforcements. Remember, in the process of preliminary sizing, we use a width of 230 mm, and this are our reinforcements that has been provided. So let's say for this case we have four Y20 at the top and four Y20 at the bottom. So this the spaces I'm talking about is the space between this. So this has to be nothing less than 20 mm, so we can have our concrete free flowing between this. And how do we calculate for this? So I'm going to pull up a calculator, and let's assume that what we have here is a total number of 4y20, which are these 4y20, and we assumed a width of 230 mm while we were doing our preliminary sizing, and we also use our link as 10 mm. Then our concrete cover was 25 mm. So I said that part is talking about the spaces between this reinforcement for the concrete to pass, the concrete sizes, the coarse aggregate to pass into the concrete formwork. So what we'll do is we'll calculate our 230, which is our total width, and we subtract our concrete cover from both sides. Our concrete cover from this side 25, and 25 coming from this point, which is 50. So we'll do 230 minus 50. So that's 230 minus 50. And also we have our links here, which is y10. So our y10 here and another y10 here. Remember, what we are going to is this point. So we have a total of 20 mm for our y10, which is our links. So minus 50, that will give us 180. Then we also subtract our 20 mm, that gives us 160 left. And now we have 4y20 assumed, 4y20 in this case. So we have 4y20, so we have to subtract this 20, this 20 mm for these four numbers of bar. So this is 20, this is another 20, 20, 40, 60 and 80. So the total diameter of reinforcement, because this is also taking up the space in this very beam. So we'll subtract this 160, 160, we'll subtract 80 from this 160, and we have 80 left. So we have three spaces that our concrete will pass into this very beam. We have this space here, this is one, this is two, this is three. So it needs these three spaces to be able to, and it will also pass through this point, but we are talking about this part as of now. So 1, 2, 3. So let's divide this 80 by 3. If we divide this by these three places to see the maximum size of coarse aggregate that can go into this beam, we have to divide this by 3 and 26.7. So this is actually okay because it is more than 20 mm. So it's always good to keep it less than 20. Sorry, more than 20. So let's come back to our software and see. And let's come back to our software and see this very beam. So if we look at this part, let's open this up, and this is our part where we have 2y16, but we practicalized earlier with 4y20. So I'll increase this size. Always look out for this point. Let me take it down. You see it's increasing and reducing. So I'll take this to 2y20. Then we add 4y20. So you see what we have here is what, 26.7. So if getting to 26.7 is already showing us a warning where that okay, we are almost getting to, you know, the size of the aggregate. So you should be concerned about your size of aggregate when you are doing this very design. Let's say what was required to achieve your proposed utilization ratio is 5y20. You see, if you use 5y20, we now have a space of 15 mm, which is not actually okay. This is not okay for design. So what can you do in cases where you is a must that you have 5y20 for you to be able to pass this beam? Now we can go ahead and create another option, which is creating a second layer of bar. So if we come here, you can see supporting top bar. This is our main top bar, and we have a space for supporting top bar here. So if we come under this place and click, if we come here and click for this supporting top bar, you see if I click this, I can increase this capacity. Now this is calculating this with this one. It is adding both of them together. Is assuming they are supporting top bar, but it's still assuming that they are on the same plane. So when we needed 5 y20 for it to pass that very beam, we can provide 3 at the layer 1 and provide another 2 at the second layer. So these two, they will be spaced by this spacer bar. A spacer bar will be provided here. They cannot be combined together, because if you add this to this point, or we add this other one and add this other one to this point, these spaces, they keep on reducing. So we have to put this at a different layer. To do that, we'll come here, then we'll come to this point. There is an option for bar at layer 1. So we'll come here and make it a bar at layer 2. So you see, it's still using the maximum here to calculate for it, but we've provided 2 extra reinforcements, and it is now at the second layer. So remember, if you just increase this, if you just add this number, it will assume that you are combining 2y16 and 4y20 at the same point, at the same layer, at the same level, at the same line. But you have to, after increasing this, or after providing this extra supporting bar, you have to come here and put them at layer 2. So it knows in the detailing it is going to provide an extra layer here. So let's come and see the detailing of this very one. So this is it. So now we have our 4y20 at this first layer, and we have our 2y16 that was provided as an extra. Let's close this up and come back to this point. Let's take this out, or let's take this to bar at, sorry, layer 1, and we'll detail this drawing. You'll see it has provided y16 extra, and this is not advisable, because the spaces between this, it comes to 9.6, and you know the concrete coarse aggregate size is not 9.6, so it cannot penetrate. So you must always look at this, because this can make have honeycomb straight inside your beam, and that means you will have something like this. If there was not enough space between the rebar for it to receive the concrete, you see inside the there will be some honeycomb inside the concrete. So this will also make you to recommend, because there are cases maybe you have to stick with a smaller size. You have to make recommendation that this beam at this very floor or this very level, ensure this is the coarse aggregate size that you will maintain for us to maintain this level of rebar arrangement. So let's go back to our structure and check other beams as well, and try to reduce their utilization ratio. So as we are done with that very one, let's go ahead and make modifications to these other ones. Let me confirm what I left here. So I will take this back to 2y16, 4y16. Okay, this is okay. I want to keep them between y16, and this, we have 4y20. No, it's not okay. I want this to be 4y16, and the utilization ratio is still high. What should we do? Okay, let's go to beams, increase this thickness 600, increase this 600, and interactive design. Okay, okay, and open this up. Okay, it has taken us to 71%. So this is 71% capacity usage. So you can go ahead and work on all of this, but most importantly, always look out for your utilization ratio. At this point, I will conclude the discussion on beams, and let's look at our column design. So I will close this up. So remember, what we've designed for is just at the story 1. So I will close this up and come to my columns at the story 1, current story, and let's see what has been provided. So utilization ratio 0.13. So what we provided was 4y16, 4y16. So I think this is okay. So let's double click. So what was provided, 4y16, this is okay. We don't have any reason to change this. But let's look at our U ratio 0.13. Very okay, 0.19. Okay. I think the maximum here is about 37% U ratio. So the beams, the columns, I don't think we have any issue with this. So this is very, very much okay for our column design. We have 416, so that means we are not spending much time here. But it's the same case. In case your utilization ratio is not enough, you can choose to increase the size of your reinforcements, or you can choose to increase the quantity. You can choose to add more reinforcements. If you come here and you type 1, you see it will increase, it will add another reinforcement. Let's It will add another y16 by this side. And if you come here and you increase, if you type 1 here as well, it will also bring out another layer on this other part. So you see, if the reinforcement that was provided was not enough, you can go ahead and increase this number. You can even increase it to 2, but at the same time also consider your coarse aggregate size while you are working with this. So this is not needed. We don't need all this. Our previous reinforcement was okay, so I will just cancel. And that is it for the column design. Then to get your design report, your checks and the rest, you can click here for the column, and let's see our report. So this is our calculation sheet. So this is our calculation sheet that actually shows our checks. So if you come to our checks here, you see this is actually okay. This is actually okay. So this is the area of steel that was required, which is 211.60 millimeter square, and our area of steel provided was 80. So this is actually okay. So you can divide this by this for us to have our utilization ratio. So I will close this up, and that's it for the column design. To also see our design reports for our beam design, come to this case, let's look at all the beams. Let's look at this is a combination of the beams on each of the story. So we'll come to, sorry, we'll come to design reports. Okay. And this is our calculation sheet for our beam design. So these are the reinforcement that we are providing. These are the checks. Our deflection check L over D. So 7.8 is less than 58.51, so it's okay. 6.51 is less than 58. So these are our checks. Our checks on the various beams. These are our checks on the various beams. So to make modification to these reinforcements, to make modification to them, what you just have to do is this part, it increases the number of the reinforcement, while this other arrow by the right hand side, it increases the diameter of your reinforcement. So this will increase this to 3 numbers of y16. If you click up again, it will increase it to 4 numbers of y16. But and now if you take this down, it will reduce it to 3 numbers of y16. While this other arrow is talking about increasing the size. So if you click this, it will increase it from 16 to 20, but still 3 numbers. And if you take it down, it will take it back to 16. So this is for the size of, or for the diameter of rebar, and this is for the numbers. So let's take this back to 2 by 16 as it was, and we click. So the next thing we're looking at is detailing. Design is very wonderful, but there is nothing as wonderful as detailing, because you can do all this beautiful design, all these reinforcements are passing, the concrete thickness is okay, but if you are not able to properly put this in a context that the artisans can read and understand what to do at every point in time, then the design is as good as you did not do anything. So detailing is very, very important. So after this class, we'll be looking at how to properly transfer this into a detailing template and properly represent them, so our artisans on site can actually see what to work with and understand what to do at every point in time, just mere looking at our piece of paper. So thank you very much for staying with us till this time at duplicate consult. We really appreciate it. If this video has been helpful to you, please do well to like it and subscribe to our YouTube channel. It helps us a lot in the algorithm, and turn on the notification bell so anytime we post new videos, you'll be notified and you can go ahead to check them. So thank you very much. We really appreciate your presence here. Stay safe till next class for detailing. Thank you and bye bye.